All right, this video is going to talk a little bit about what we call Gaussian elimination, but in order to talk about a new method of eliminating equations, eliminating variables in order to solve systems of equations, let's review what elimination was to start with. Remember, the method of elimination basically said if I add two equations together, I would like one of these variables to be eliminated, such as if I add the x's to the x's and the y's to the y's, again, I want one of those to disappear. Now, you'll notice these numbers aren't opposites. But if I adjust my numbers, right, if I multiply my top equation by 300 and my bottom equation by negative 200, right, all three parts on both sides of the equal sign, perfectly legal, then you'll get 6x minus 6x, and we'll quickly be able to solve for y. Again, you should be familiar with the method of elimination if you're watching this video here. Then we'll take our y, we'll plug it back into another equation, and again, we'll go get our x value. Again, this is a consistent system, purely because we got an answer, and it's also an independent system. We got a single answer. Dependent would have meant we'd have multiple solutions, and inconsistent would have meant no solutions at all. But again, we got a single coordinate, right? We got x equals 16, y equals 14, one coordinate, very simply, right? 16, 14, where those two equations, those two lines, would cross on a graph. Now, you can use that sort of last idea of back substituting even if you have more than one variable. And we can use these other ideas as well, but if we already know we can solve for this variable z, right, we can take z and plug it back in. It's very helpful that we have this second equation that only had a y and a z in it, because we plug in z and then we could quickly solve for y. Now, if I know y and z, I can plug those into that first equation. Notice it only has three variables, but I know two of them. So now I can quickly solve for x. So it's helpful to have this sort of stair-step pattern going on where we have a single x term. The next equation doesn't have an x, but it has a single y term, right, that we can go plug in because we knew what z was from that last equation. We get this stair-step idea. And that's really the idea of Gaussian elimination. Gaussian elimination is a process of using row operations, elementary row operations. Basically, we can switch equations, we can multiply equations by a constant, and we can add equations together, but it's using those three ideas to stay organized when we're trying to solve a system of equations. Our goal is going to be to reach row echelon form. That's that stair-step pattern I just talked about. So let's go ahead and try this out, and we'll see what Gaussian elimination looks like. So we've got our whole system over here, and the first thing we're going to do is we're going to sort of start adjusting it. So I'm just going to draw a little arrow so that we can write down what we're going to do, and then I'll be able to reorganize, right, our whole system as we go here. Well, first thing I notice is that rows 2 and 3 would be really easy to add together and eliminate x, right? So that's one thing that I'm thinking about doing. But remember, I still want to have an x value when I'm finished over here because I need to be able to stair-step back. I need to be able to go get that x. I don't want to eliminate all the x's. But this equation would also be really nice, knowing that that's just a single x there without a coefficient. I really like the idea of having a 1x in that upper corner. So what I'm going to do first of all is just write row 3, right? As is often notated here, you would sort of switch row 3 and row 1. But I'm just going to write row 3 up here again. So x minus 2y plus 3z equals 9. Then, in addition to that, right, now I'm going to think about, hey, I want to add row 2 and row 3. So I'm going to take row 2 plus row 3. So I'm going to add those two together. Well, negative x plus x, x is gone. 3y and negative 2y makes for a 1y, which is a good thing. And no z, right? There isn't a z here. 0z plus 3z would just be 3z right there. We're also going to add our constants on the other side. So negative 4 and 9 would have been 5. And that is going to be our new row. And now this is where it gets a little bit tricky. Using this row sort of notation, I'm just going to assume that I know that that's row 1 and row 2 and row 3. Our names are sort of going to change. I'll show you a way on the next screen to sort of work around that a little bit. Now, In the bottom row, I also don't want to have an x, but again, I can't add the same two equations because I would just get the same equation back again. So I have to use row 1 here. So as long as we have a positive 2x and a negative 1x, why don't we go ahead and take row 1 and let's add 2 times row 2. Because in that case, we'll do a little side work down here. We'd have a 2x minus 5y plus 5z equals 17. 2 times row 2 is negative 2x plus 6y plus 0z still, and again minus 8. And if I add those two together, right, we end up with, again, just a y. We get a 5z, and we end up with 9 over here. So again, that makes for a nice statement on there. Now we have our x sort of all ready to go. Now we're going to move our way down the stair step, right? We've handled x. We've got 1x here. We've got nothing below it. Now I'd like a 1y right here, which I just happen to have. If I didn't, what I would want to do is multiply, operation number 2 here. I would just multiply by a fraction to force that to be a 1, right? But since I've got that, we're in good shape. Let's go ahead and move on to the next step then. Again, I like our first equation, so I'm going to keep that. So we just rewrite that very quickly. I like our second equation, so again, I'm not going to lose that one. I like that idea. But what I want to do is get rid of the y that's right here. I want to get so we can solve for z. Well, since this row, right, is already a positive 1y, why don't we go ahead and just take row 2 and subtract row 3. Y minus y will disappear. That'll be 0y. 3z minus 5 would be a negative 2z. And again, 5 minus 9 would just be simply negative 4. Let's go ahead and go down here, and we'll keep on traveling here. Now we're sort of in row operation, or row echelon form, right? We're in that row echelon form. Sorry about that screen opening up there. But if we're in row echelon form here, x, y, down to z, we've got that stair-step pattern going on, right? What I want to do now is solve for z. But I'd like that to be a 1z. So I'm going to go ahead and just do this one more time. What I'm going to do is take row 3, and I'm going to multiply it by a negative 1/2. By a negative 1/2. Because again, I still like row 1. I still like row 2. But if I multiply that bottom row by a negative 1/2, I'll get z equal to 2. And that is the first part of our answer. After that, what we can do is back substitute again, like we did on the previous screen. Why don't we just take y plus 3 times 2 equals 5. Well, if y plus 6 equals 5, then y equals negative 1. And now we go back to the first equation, right? X minus 2 times y plus 3 times z was equal to 9, which means positive 2 plus 6 would have been x plus 8, and x equals 1. And we have our answer, 1, negative 1, 2. Again, the idea of Gaussian elimination is mostly to use these row operations to keep track of what you're doing from step to step to step. You do need to rewrite the entire system when you do this, because again, this is just that's the method of organizing sort of what we're doing. But once you get to REF, right, this is that row echelon form, right, REF as we call it, where we have that x down to the y, sorry about that, where we have this x to y to z, then you can back substitute. Then we can just plug our numbers back in and finish the problem. Go ahead and try some of the problems in your homework, or if you want to, you can watch another video. I'll make another video on with another example in it, just showing us again another way to do Gaussian elimination.